So, a difference between electrochemical reactions versus this reactions. Okay? Okay. This stands for electrochemical. Okay? EC. It's short for electrochemical. Is that you can control this with you can control the rate of this reaction. Okay? With down the voltage. And I'll explain. Okay? Because this is okay. So so previously, okay, we talked about the how U, okay, this is the equilibrium potential, right? Right? Okay. This is when at I is equal to 0, right? There's no current, right? So now we're going to talk about when so let me this is potential, okay, at I is equal to 0. Okay. So now we like to know what I is. Okay. When I is not equal. Okay. Okay, so normally, okay, when we have a metal, okay, and we dip the metal in a solution, okay, usually most metals, okay, they will have a charge. Okay, it doesn't matter if it's connected to another piece of metal. Okay, so because the presence of this charge on the surface of the metal, okay, if it's within if it's dipped inside an electrolyte, okay, the electrolyte will spontaneously form align its ions to form what's called a doublet. Okay? So this is a doublet. Okay? Doublet. Okay? And there is a potential difference here within this doublet. Okay? And even when there's no current. Okay? So equilibrium, okay? Equilibrium. Okay? This doublet, okay, has a potential. Okay? This potential is characterized by this delta phi. Okay? This delta phi is equal to the potential of the metal minus potential of the solution. Okay? This is short for solution. Okay? And this is equal to U. Okay? Equilibrium. Okay? So looking closely at this doublet, okay? If we blow this up, okay? Okay, this is the metal, okay? And it has this negative charge. so, if we have an ionic solution, okay, if you look very closely at this, okay, this, if it's going to have if it's an ionic solution, then you will have different ions, okay? And cations is going to be surrounded by water. This is water, okay? This is H2O, okay? And these water forms a hydration shield, okay, around the cations, okay? And then, because the anion is smaller, okay, there's less water around the ions because it's small, okay? And so, there's a length scale, okay, here that is relevant, okay, for looking at the potential difference between the metal and the electrode, okay. So if you look very, very closely at the atomic level, okay. So these are water, okay. They will form. They will align itself, okay, and these ions all at the layer, at the double layer, okay, of at the double layer region, okay, and so. So the distance away from the metal, okay, is there's a relationship between the potential and the distance away from the surface of the metal, okay. So if you look at this Vm, okay, which is the potential of the metal, okay. So this is okay. This is where the Vm is. Okay, that's it. Okay, it has a high value. Okay, so let's call this Vm. Okay, and it's going to decrease like this. Away from the surface, okay, of the metal, okay? And then, I think out here, okay, now so they have different layers, okay? So, from the midpoint of these first anions, okay, this is called the inner Helmholtz point, okay, and then from here to the midpoint of this cone, okay, this is the outer Helmholtz point, okay, the inner Helmholtz. I'll write this out. Inner this is from the midpoint of the anion to the surface of the metal, and this is from the midpoint of this cation to the surface of the metal. So most of the potential loss, okay, is pretty much within this distance, okay? And here, okay, approximately to this is not zero, okay? This is probably VS, okay, which is the potential of the solution, okay? Okay? So, so from here to the point where the outer Helmholtz line is, okay? This distance is roughly 22 nanometer, okay? So it's very small, okay? And then the next, and from this point to where it pretty much, you know, like diminish to the point of the V of the solution, where's where the potential of the solution is, okay? Is the edge of the this is the outer diffusion plane, okay? Where the diffuse double, okay? This is called the diffuse here, and this is diffuse double. Where the potential pretty much equilibrate to the potential of the solution, okay? Okay? This is short for solution, okay? So, this distance right here, okay? To the edge of the diffuse double layer, this distance is roughly 50 nanometer. Okay? Okay. And then the diffuse part is double layer. I'm sorry. This is 10 nanometer. Roughly 10 nanometer. Okay? So this distance is roughly 0.2 nanometer from the edge of the metal to the midpoint of the reverse cap. Okay? And then roughly 50 times this distance, which is 10 nanometer. Is the edge of the diffuse double layer, where the potential diminished to the point of the solution. Okay? And then, and this distance right here, okay, is, it has a special name. It's called the dividing. Okay? And it's beyond the divide line, okay? You don't feel the effect of the metal anymore. Okay? You don't feel the potential of the metal anymore. Okay? And then another link, that is relevant, okay? And now I'm gonna put a stop right here, okay? Because it goes much, much higher than this, okay? This is roughly, this is 1 millimeter. Okay, this, this is the, this is the length of diffusion length. Okay? This is visible to the eye. Okay? Okay? So most of the, so most of the, most of the loss of potential, happens like within the very short distance away from the edge of the metal. Okay. So. So, to do a quick derivation, okay? So we have a positive charge, right, within the solution, okay? So, this is potential in solution due to charge. So this is the combined. Okay. So consider the solution of ions. Okay. So if you have an ionic solution, okay, like these, okay, this is out here, okay, we have an ionic solution, okay. We have positive charge and negative charge within solution, okay. So what happens is that, because electrostatic repulsion, the positive charge sees a positive charge is going to bounce off, okay, because that electrostatic repulsion is very, very strong. But the anions is going to be drawn to it. Okay? So we have two type of electrostatic repulsion interactions. Okay? We have electrostatic interactions. Okay? So we have positive, positive. This is repulsion. Right? And then we have negative and positive. This is attraction. Okay? So, this electrostatic interactions will increase this will decrease uniformity. Okay? Because it's going to order, like the negative charge is going to order around the positive charge or charge like this, okay? Whereas temperature, okay? Temperature, the increase in temperature will increase uniformity. Okay, due to the increase in Brownian motions. So the hotter the temperature is, the more these charges don't wiggle, okay? The more they wiggle, the more uniform it's going to become. Make sense? Yeah? Okay, so this potential, okay, due to this electrostatic interactions and temperature, okay, okay, can be summarized. Okay, so this the potential dissolution is a function of electrostatic interactions. Okay, and Brownian motions. Okay. Right? Okay. And so to quantitate this, okay, we have Ci, okay, which is the concentration initially, and then Ci infinity, which is the reference. Okay, this is the reference concentration. Reference concentration at O. Okay, is equal to exponent minus Ci.
然后所以是温度上升，它的电温会变高，solution的。
不对，温度上升的话，这个 Brownian motion 就是它会这样子晃动，是一种entropic 现象，就是熵增的现象，对吧？所以它会，你想想，如果温度越低的话，这个东西会靠近它以后它就不想走。但是温度高的话，它靠近它以后，它就比较有机会走。然后这个温度高的话，它也会比较有更多的就是 probability 接近它。
那对电会有什么影响？
看这个就知道。
哦，好。
好吧。这是 RT。这之前我们讲过这东西是什么，对吧？这个是 this is the charge number, right? This is the Faraday's constant, this is potential, okay, over RT, and this is the concentration. So concentration is not a function of temperature, okay? And this right here, okay, this is work required, okay, to move a mole of ions to a different energy state. Okay? So the boundary conditions, okay? C equals to C times infinity at when potential is equal to 0. Okay? When this is equal to 0, exponent is 0, Ci equals Ci infinity, right? Yeah? Okay? Okay, so to solve for this, okay? So because this is a spherical geometry, okay? This is so to solve for the potential distribution okay of ion in solution is given Poisson equation, okay, which is in spherical geometry is this, okay, minus rho e over epsilon minus epsilon so this is relativity, okay, which has C over E. Coulombs per volts per meter. Okay? So this is spherical. This is spherical symmetry. Because this is spherical, right? This is the solution, so this is spherical symmetry. Okay? Have you guys learned transport? 还没有是吧？这就是有4种，有 rectangular geometry, spherical geometry, and radial. Okay? To solve for this, okay, so this is spherical geometry. Spherical geometry. If you were to solve this using spherical symmetry, the solution is 1 over r squared, ER. R squared ER. Okay? This is spherical symmetry. Okay? For the spherical symmetry solution for this. Okay? So this is minus rho e over epsilon, which is equal to minus f over epsilon sum I, Ci. Okay, you substitute this. Ci is equal to Ci infinity times this. Okay? So you substitute the Ci with this. Okay? So Ci infinity exponent minus z f. Okay. So this I is sum over these ions in solution. Okay. So sum over each ion in solution. Okay. So the boundary conditions, okay? As R goes to infinity, okay, potential is equal to 0. Okay? Makes sense, right? So if this positive charge is if this positive charge is very far away from this, then the potential felt by these two charges is equal to 0, right? Same for the negative charge. Whatever interactions between two charges, if the R goes to infinity, the potential, which is the coefficient of them, goes to 0, right? Yeah? 啊？
可以用中文讲一次吗？
就是这有2个 charge， 对吧？当它们中间的那个什么distance 变长的话，它们就看不到彼此了。
哦，
那它们中间的interaction 都是牵出去的，
对，
对吧？然后 when R is equal to A, okay, EP, PR, and R is equal to A is equal to minus Z, CQ over 4 minus epsilon A squared. So this is the charge density, okay, integrated throughout the volume surrounding the central atoms. So this is the okay. So if you were to solve this equation using these boundary conditions, okay, there's some math, okay, 需要一些数学，数学会比较复杂，我就不在这边说了，okay. So using Gauss, so using Gauss, okay, Gauss is all, okay, and variant series. Okay. 这个东西 ，okay. Exponent minus zi.这个等于这个差不多等于 one minus okay. So using mathematical operations, they found that this part is roughly equal to 1 minus that. Okay? Okay, so if this is the case, then so 1 over R squared E dr R squared E dr So this right here, okay, do this operation to simplify to this, okay? This is mathematically equivalent, okay? And then if you multiply these two within, okay, you get minus that epsilon z I infinity, right? Plus So this is a very big number, right? It's a very big number, right? Birthday is on 96485, right? This is the power square, right? So this is, because the square is much bigger than this, right? So this can be reflected, okay? So if that's the case, we get that square, epsilon RT. Okay, about epsilon. Y. C squared CL. Okay. So this is equal to B over lambda. Okay. So lambda is equal to epsilon over AT, epsilon over RT. Squared pi squared. Okay, so this is the dividend. Lambda is equal to the dividend. Okay. Oh, sorry. Square. Okay.
可以，我现在在算什么？
什么？
现在在算什么？
I derived the dividing.
我是从前面这边在算。
对，这就是要给你看这个 dividing 是从哪里来的。这是 dividing，
发人是指
就是这个 distance， 从这边到这边。
好。
Okay? So this concentration is going to diminish the dividing. Okay? And this potential is going to diminish from phi metal to phi solution in the dividing. Okay?你哪里看过？
那个
你要不要上来试一下？
应该是 by solution 然后减上去的那一点。
你大声一点好不好？你过来指一下，我看你在讲什么。
by solution 的那个 servant 还是 solution， 然后
这
减。
里这边是吧？
对。
这是 electrostatic interaction。 Electrostatic interaction， 这个是 Brownian motion。Brownian motion。
information 那边我看不懂。
这个是什么？
对，你现在指的地方就是我看不懂。
这是一个 period， 这是一个。
不是，这只是字我看不懂而已。
是 electrostatic interaction。 好吧。Okay, so 所以你有这个东西对吧？So 1 over r squared d dr r squared d dr is equal to v over lambda squared, okay? V over lambda squared is equal to epsilon RT S squared I squared okay? Which is equal to V over lambda squared, okay? So we have a second order partial differential equation using these two boundary conditions, and we can solve this. Okay? Okay? So we can solve this second order partial differential equation using these two boundary conditions. Okay? So the solution, okay, is V is equal to ZCQ, okay, 4 pi epsilon r exponent A minus r over lambda 1 plus A over lambda. Okay. So this is the change in potential as a function of r, the distance away from a charge, okay? The charge in solution. Okay? Okay? So this is a function. Okay. It's a function of this r. Okay. Right. It's a function of r. Right. Yeah. And also the function of lambda, okay, the dividend is a function of this, right? The permissivity, which is a function of the electrolyte, the ions on electrolyte, temperature, okay, concentration, okay, and charge, okay, okay. So as lambda decrease, okay, with increase in concentration, okay, let me write this. So as concentration increase, okay, when concentration increase, this will lead to lambda decrease. This concentration increase down here, this is going to get smaller, right? With this number becoming bigger, this lambda is going to get smaller, right? So lambda is going to become smaller, okay? And this will result in shielding, okay? Shielding. So, which means, okay, this is the potential, okay, which is in volts, okay, the solution, okay. So, and this is distance, okay, and in nanometer, okay, roughly in like 10 nanometers, okay. pretty much by 1 nanometer, like because the shielding, you don't see the interactions between ions and ions anymore in solution. Okay? With increasing concentration, okay, this effect is even more severe. Makes sense? Yeah? Okay. So, okay. Okay, so keep this in mind, okay? We have the inner Helmholtz layer, which is the outer Helmholtz layer, okay, which is 0.2 nanometer, okay? So most of the potential difference between the metal and the solution decay within the divider, okay, which is roughly 50 OHP times OHP, right? 50 times OHP. The distance of the OHP, outer Helmholtz layer, is roughly 0.2 nanometers. So roughly 50 times that is 10 nanometers, which is approximately the divider. Okay, right, in the charge solutions. This is concentration dependent. Okay, this is in a 1 millimolar solution. Okay. In a more concentrated solution, the divider length is going to drop. Okay. So, the electric field, is force felt, okay, by unit charge. So delta V, okay, this is equal to times E times D, okay? This is an electric field, okay? This is distance, this is the charge, the voltage, okay? So, electric field, okay? Flow from high to low voltage. Right? So here's high voltage, here's low voltage, so the electric field flows that way. Yeah? Yeah? So therefore E is equal to delta V minus D, right? Yeah? So if you have 1 volt, so each G, okay? For 1 volt, if you have 1 volt, okay? Okay, if you have 1 volt, okay? Then, so if your metallic conductor, okay, is equal to 1 volt, okay, right? And then, I'm sorry, delta V, okay, delta V, which is equal to 1 volt, okay, 1 volt. Then your electric field, okay, this is E is equal to 1, okay, divided by, in our, 1 millimolar solution, okay, for, in 1 millimolar solution, okay. This is 10 nanometers, right? So it is 1 times 10 to the negative 8 meters, okay? So you get 10 to the 8 volts per meter. Okay? Right? So this is a large charge. This is relatively a large electric field. Okay. For this. So we have reaction, okay? We have a reaction, okay, that's a function of the voltage. Okay? The reaction rate is a function of the voltage, okay? So the rate of reaction at surface, okay, right, is proportional to the rate of electron transfer from ions in solution. Okay? Then at equilibrium, okay, we have delta V is equal to E metal minus E solution, which is equal to U. Okay, this is the equilibrium, okay? Yeah. This is the open circuit potential. This is equal to U V cell times R E N L. So, but this is when I is equal to 0. Okay? Right? So what if I is not equal to 0? Okay? We'll do some examples. Okay? So examples. Okay? So we have a solution. Okay? So Ft 2 plus and Ft 3 plus Ft solution. Okay? Solution. You look this. Okay? So So within the solution, okay, there's Fe2 plus, okay, and Fe3 plus, okay. So based upon the potential, okay, this is the potential of the metal, okay. We can't really do anything with this, right? The potential of the solution is fixed, right? But we can change this potential of the metal using a potential step. Okay? So we can increase the potential or we can decrease the potential by the dot. Okay? We can determine it. Okay? So this has equilibrium potential or open circuit potential. Okay? So that's U, right? This is U. Right? This is the equilibrium potential related to these ions, right? So if we increase the potential of the metal, right, we will decrease the energy of electrons, okay, in metal. Okay? So this would lead to, so this will happen, okay? So the Fe, so the metal would, so if we do this, okay? If we increase the potential, this is what's going to happen. This is going to drive another reaction. This is going to drive reaction, reaction in another direction. Which is the oxidation. Okay. What does that mean? That means this reaction is going to happen. Fe2 plus is going to go to Fe3 plus E minus. Okay? Fe is going to give off electrons to the middle and then become Fe3 plus. Okay? Now this is oxidation, right? I'm going to write that one here. This is oxidation. Okay. If we decrease the potential of the metal, okay, we're going to increase the energy of the electron. Metal. Okay, this is going to drive reaction in cathodic. Reduction. What's reduction? Reduction means the electrons on the left-hand side. Okay? So Fe3 plus electron is going to Fe So if you increase the potential, okay, this is gonna drive it in the, you're gonna drive the, oxidation reaction, okay? Whereas if you decrease the potential, you're gonna drive reaction in the reduction reaction. Reduction means whatever is being reduced, okay? Reduce means you're gonna take up electrons. Oxidation means you're gonna give up electrons. Okay? So, an example, okay? So, this is example 3.1, okay, in your book, okay? So you have two inert platinum, okay? In a solution with Fe2 plus and Fe3 plus. Okay? And so with the reaction, Fe3 plus electron is equal to Fe2 plus with equilibrium potential of 0.771 volts. Okay, this is from your appendix A, right? This is from your appendix A. Okay, so this is the standard reduction potential. Okay, so the question, the first question is, what will reaction be reduction or oxidation? Okay. Is 0.44 volts. Okay. Feed metal if feed metal is applied. Okay. If you apply 0.44 volts to this solution, okay, with two platinum, okay, inert platinum, okay. Both these are platinum, okay, they're inert. Inert means that they're not gonna react, okay, they're just gonna conduct electrons, but they're not gonna react, okay. So the first question, will reaction be reduction or oxidation with the metal? Okay, the potential of the metal is 0.44 volts. Okay. So you draw your okay, this is U of the metal. Okay, this is at 0.44. I'm sorry. This is the equilibrium potential for this reaction. Right? This is at 0.77 volts. Right? So the potential you apply to the metal, okay, is, it doesn't say which one, but whichever one that you apply is the, this is 0.44 volts. And this is the metal. Right, you apply this to one of the electrodes. Okay, so is this higher than that, or this is lower, right? Obviously, right? If this is lower, what does that mean? Okay, so because we're lower than the equilibrium potential, everything above is going to be in the anodic direction. Okay, this is anodic direction means it's going to give off electron. Okay? And then everything below the equilibrium potential is going to be cathodic. Okay? This is going to require electrons. Okay? The electrons on the left-hand side. Okay? So because this is the reaction, okay? So it's going to be Fe3 plus electron goes to Fe2 plus. So this is the reaction that's going to occur. Make sense? So the second question is, okay, will iron deposition occur? Iron deposition. Iron is Fe. I'm charged. Okay? Will this occur? Okay? So the iron deposition is a different reaction. Okay? It's Fe2 plus 2E minus is equal to Fe. And this has an equilibrium potential or a standard potential of minus 0.44 volts. So minus 0.004 volts. Okay? So you draw this again. Okay? This is this reaction. Okay? This reaction has the equilibrium at minus 0.44 volts. Right? So anything above this is in the anodic direction. Anything below this is in the cathodic direction. So anodic direction means that the electron's on the right. Right? So because we're at point where the female is here. It's above this minus 0.44 volts. So we're in the anodic phase. Yeah? So if this is an anodic phase, and that means the electrons on the right hand side reaction. Right? So so the reaction that's going to occur is Fe2 plus I'm sorry. Plus 2E. Okay. So this is the reaction, right? The electrons on the right hand side, right? So because we're in the anodic region, okay? So we're in the anodic region, deposition of iron is on the cathodic region. So deposition will not occur. Right? Okay, the third question. Okay. Well, hydrogen evolution occur. Okay. So again, we draw this. Okay, the hydrogen evolution H2 goes to 2H plus 2E. And this has the potential, standard reduction potential of 0, right? And this reaction has a standard reduction potential of 0. Okay, this is the definition. So U is 0, right? Right? And the female is at 0.44 volts. Again, we're in the anodic direction. We're in the anodic region, right? Anodic region means that the electron is on the right hand side. Okay, so this is correct. So hydrogen evolution is on the left hand side of the reaction equation. So hydrogen evolution will not occur. Make sense? sensor. You good? Okay. Any questions? Okay, and we'll stop right here.
这些东西都会录下来放到网上，你们